Hello, my name is Colt Correa. I'm the COO of Intrepid Control Systems, and this video is on Automotive MACsec and MACsec Key Agreement, otherwise known as MKA. We've recently added an entire section to our Automotive Ethernet book, now in its second edition, about automotive cybersecurity. And this is one of the new chapters in that book. I hope you find it interesting. Software-defined vehicle has become a very popular term recently. And when we look under the hood, what does it mean from an electrical architecture standpoint to have a software-defined vehicle? In most cases, it means that you have a central compute system that is a high-powered computer that makes most of the decisions for the vehicle. And the actuators and sensors then are often remote from that. And what we have is essentially an architecture where we do a lot of remote control and a lot of remote control over the network. And this type of architecture requires a significant amount of bandwidth, and the only network that really supports the flexibility and the bandwidth is really Automotive Ethernet. So we're seeing a big increase in the popularity of Automotive Ethernet as a backbone to a lot of vehicles. And as a result of this, there was an interest to protect that backbone against attackers. And one tool that we can use for that protection is MACsec and MKA. MACsec is defined in IEEE 802.1AE, most recently updated in 2018. And MACsec Key Agreement, MKA, is 802.1X, most recently updated in 2020. Both of these specifications were developed without a lot of automotive requirements in mind. Because of this, there are certain aspects in the specs that don't fit automotive requirements, specifically timeouts and latencies. So an automotive group within the Open Alliance group formed a technical committee 17, TC17, to adapt these two standards to automotive use cases, and essentially reducing timeouts and latencies and simplifying the implementation to a significant degree, especially for MKA, where you have, it was originally designed for large enterprise systems where pieces are being added and removed after the fact. So there's a lot of dynamic configuration nature in MKA, whereas in an automotive setting, you have a pre-engineered network and you're not adding and removing nodes after the fact, after the vehicle is produced. Because of this, the MKA and MACsec is reduced in complexity compared to the original standards when we talk about the automotive use case. And the MACsec itself standard is for the protection of the communication. It is point-to-point. And in the automotive use case, it's really PHY to PHY. In other words, you take a automotive PHY, a chip that supports MACsec, and it will communicate to another PHY, and the protection is between the two PHYs, where the PHYs actually do most of the heavy lifting on the calculations. That means every PHY pair in the network gets its own unique key and has its own unique protection point-to-point. But the MACsec, it does provide very good protection for essentially any traffic that you want to protect. We can have a filter in the PHY to bypass certain MAC frames, or we can protect all MAC frames. And what MACsec provides is, first and foremost, authentication. That means that all receivers can know for sure that a received message is from a good, authentic, and intended source. Integrity means that we can detect any changes. If the data is changed in transit by any entity, we can detect any changes of the data itself. And MACsec also does provide encryption, so it's optional and used sparingly in automotive use cases, but encryption of data is also possible with MACsec. And as we'll see as we go through, it's a system that also provides very good replay protection, so that a third party, a malicious third party, does not have the ability to record data and just replay it back on the network. So MACsec is essentially the protection at layer 2 from point to point, PHY to PHY in the automotive use case. And the MACsec Key Agreement, MKA, is the specification that defines the key delivery system. As we'll see in MACsec and MKA, the best protection is when you use ephemeral keys, temporary keys that get distributed and rekeyed and changed out over time. So we'll discuss all these details as we move forward. Okay, here's a list of acronyms that we're going to commonly use in this presentation. Again, this is a short list of acronyms. There are many more that I'm not going to cover, and I'm going to try to avoid acronyms as much as possible. Connectivity Association is a grouping of all MACsec participants that share the same CAK and CKN. CAK is the Connectivity Association key. This is the main secret. This is what you want to hide. It's going to be, in automotive use cases, pre-stored securely in secure memory within all participants of a MACsec protected network. The CKN is just a name associated with the key that's given to it. It's often a text name. It doesn't have to be a text name. There's no rules around the name. There's no naming convention for it, but it does have to be unique for the network associated with a specific CAK, the Connectivity Association key. And a secure association is a unidirectional, only one direction, point-to-point or PHY security context used to protect MAC PDUs inside of MACsec PDUs. The Secure Association Key, SAK, this is the main key that's used within MACsec to either encrypt or authenticate the frames as they come in. It's an ephemeral key. Ephemeral key means that it is temporary. And the SAK is generated from the CAK as one of its inputs. The SAK is ephemeral. The reason why we use ephemeral keys is because the SAK needs to be distributed and actively used for the protection on the network. And by using a temporary ephemeral key that will get swapped out when certain conditions happen, means that, first of all, there's not enough information or data transported with an SAK to be able to reverse engineer the SAK itself mathematically. So that's one way of protecting it. It's not used long-term, it's only temporary, and by using it only temporary, there's not enough data to reverse engineer a key. Secondly, using an ephemeral key like the SAK and not the CAK directly, which is your main secret, it hides the CAK. So you're not using the CAK directly, and therefore it provides an extra layer of protection to protect the main secret within the network. And a MACsec PDU is essentially just a modified standard MAC frame with added information, the sec tag, and the ICV to secure the frame itself. So MACsec PDU just means a secured regular MAC PDU with additional information. That additional information is the sec tag, the security tag, and the integrity check value. So those two terms we're going to cover in detail as we go through. The ICV, integrity check value, is the output of a cryptographic calculation used to authenticate the MAC frame. So now moving on to specific terms for MKA, we have an MKAPDU. These are special packets of data transferred over standard MAC frames that contain information needed for MACsec Key Agreement to occur. And keeping in mind, MACsec Key Agreement, what its purpose is overall is just to deliver the SAKs, deliver the ephemeral keys. MKAPDU job is essentially to take the CAK, the main secret, have a key server, calculate ephemeral keys, and distribute those ephemeral keys protected across the network when it needs to, and the keys go to the right spot and get activated at the right time. We'll go through all this as we go through the presentation. So that's an MKAPDU. The ICK is an integrity check key. This is a key that's derived that is used for the authentication of MKAPDUs. The KEK, key exchange key, this key is used to, also derived from the CAK, used to encrypt the transport or hide the identity of the SAK. So the SAK is ephemeral, the secure association key. It's the one used in MACsec PDUs for protection, and that key is generated by a key server and sent over the network. In order to protect that key from being seen, its identity must be hidden, therefore encryption must be used. The KEK is used for that. And then we have a KDF, key derivation function. These are the functions that are used to create the ephemeral keys, the KEK, the ICK, and the SAK used by MACsec, all from, as one input, the CAK. As I go through the presentation, I'll do my best to avoid complicated acronyms and special terms, but to avoid all of them is not possible. These are a short list of ones that are very important that you should know if you claim to have any knowledge of MACsec and MKA. Within MACsec and MKA, there are a number of configuration parameters, options, timeouts, and other things that must be configured and agreed upon by all participants in order for them to function properly. The overall strategy of how everything is configured is called a security policy, and some of the main items are, for example, how do we provision a CAK? In automotive use case, we pre-store the CAKs. What is the format and actual name of the CAK, the CKN? How do retriggers occur, or what triggers a rekey event? Main thing would be when a packet number is close to rollover, but you can also trigger based on time and other things. How long does a key remain viable after a new key has been generated and installed? That's the SAK retire time. Whether we're using confidentiality, whether we're doing encryption or not, and if we're doing encryption, what data do we encrypt? Whether we're using extended packet numbers or regular packet numbers. Extended packet numbers take a longer time and don't roll over, so it reduces the amount of rekeys that have to happen. How fast do peers need to send messages out to be considered live, and what is the timeout if a peer doesn't send a message? How long do we wait before we consider the peer inactive? Message interval, how often do we have to send messages? Cipher suite policy, everyone has to agree upon a cipher suite to be used for authentication and encryption. Whether we're going to bypass certain MAC frames based on ether type or MAC addresses or VLAN tags. What happens if some system doesn't support MACsec? What's the fallback mode? Are we still going to allow messages? Are we going to block them? All of these things comprehensively put together is called a security policy. Generally, there's a person or a group of people that define the strategy for the cybersecurity system, and they generally put together the security policy that all participants have to follow in order to work together. And as we go through the presentation, we'll be touching on various aspects of these different configuration parameters as we talk about the specific details of each part of MKA and MACsec. Here's the overall architecture for an automotive MACsec node. First, we have the PHY with the built-in MACsec engine. The PHY itself, with special hardware, does the heavy lifting of the calculations for the cipher suite at wire speed. This is done to offload any burden on an SoC or host microcontroller. The MII interface, Media Independent Interface, is a standard interface that's used to transfer standard MAC frames into the engine that then get processed. The engine, though, however, also needs configuration parameters, part of the security policy, as well as the ephemeral keys that are used, the SAKs. This information is transferred generally over a separate interface, which is called MDIO. So we have a host microcontroller with a media access controller sending frames in and out of the PHY through an MII interface. And with MDIO, we can read and configure the PHY for the particular security policy that we're implementing for the MACsec. The cipher suites that are possible for MACsec are AES 128, AES 256, and GCM mode. And we also have an option for extended packet numbering. So in the first two, we have a packet number that is the 32-bit number, and in the second two, we have a 64-bit packet number. The packet number prevents replay attacks, so that every time a transmitter transmits a MACsec PDU, it increments the packet number, and the packet number can never roll over. So a 64-bit packet number will last a lot longer than a 32-bit number. But of course, the 64-bit will consume more bandwidth for the security as compared to the shorter 32-bit. Here's the overall architecture for two MACsec-capable entities communicating to each other, one sender and one receiver. First, we have the sender, host, or SoC or microcontroller, and it generates essentially media access controller frames through a Mac controller that's inside of itself. And generally, those unsecure normal Mac frames are sent through an MII interface into the PHY. Prior to MACsec becoming active, an SAK, an ephemeral key, must be sent to the MACsec engine inside of the PHY, and generally this is done through MDIO. And this also occurs on the receiver side, where it receives the same key as its communication partner. So here, inside the Mac engine, the decision is made, should certain frames be protected or should they just be bypassed and sent unsecurely. That's based on what's called a permit policy, which is part of the security policy. For frames that do get protected, they get additional information and integrity check value, as well as a sec tag, and sent over. And this is a secure, what is called a secure channel. It's unidirectional. If we want bidirectional communication, then the receiver also has to open up a separate secure channel to the sender in order for bidirectional communication to happen. And that's the typical use case. That is normally what happens. So secure frames are sent over the secure channel, and then on the receiving side, the permit policy decides, does this frame need to be processed in any way? If not, just gets bypassed to the MII. And if it does need to be processed, then the MACsec engine inside the receiver PHY with the same key, the same SAK as the sender, then will verify that this is a good and valid frame, strip off the additional information, and send it back up through the MII on the receiving side. There is what's called an association number associated with the SAK. It's a 2-bit number, 0 to 3, and it's used to associate a secure channel with a particular key, a particular SAK. And this is used in the rekey process, where if a new key needs to be sent into the MACsec engine, the association number is incremented, and it gets a unique one, and that association number with the SAK creates a new channel that can be used with the new key and new association number at the same time that the old key and the old association number can be active as well for a short period of time, so that communication is not interrupted during the rekey process. And we'll go into detail how that works as we get into the MKA part of this presentation. So here's what a MACsec PDU looks like. MACsec PDU is just a regular Mac PDU, a Mac frame, with additional information. 2 pieces of information, which are the sec tag and the ICV, the integrity check value. The integrity check value is either 16 or 32 bytes long, depending upon the cipher suite that is selected. And all this is the output of the cryptographic calculation that does that you can use to validate, to authenticate the entire frame. And the authentication data that goes into the ICV calculation is the most of the frame, the destination, source address, including the sec tag, any VLANs, the original ether type, and payload. And then when the MACsec PDU was created with this additional information, a new frame check sequence has to be calculated on the Mac frame in order for it to be the correct value for the new data. The sec tag contains, first of all, an ether type. Ether type is always 88E5 for MACsec. This indicates that this is, in fact, a MACsec PDU. There's some tag control information with flags about the originator of the message. The association number that we just spoke about, this is so that the receiver can know what association number is being used, and this association number is used to look up the correct SAK key in case there's multiple being used at a particular time based on what the transmitter used. So the transmitter sets the association number. The receiver uses the association number to look up the correct key. There is a short length used only for frames that are less than 48 bytes. We don't need to cover that here. And then a packet number. Packet number is very important. This prevents the replay attack, and it's either 32 bits or 64 bits in the case of extended packet numbering. And then we have an optional secure channel identifier, which is typically just the transmitter's MAC address, which is 6 bytes, plus a 2-byte number called a port identifier. And this is just a number assigned by either MKA or MACsec. It's not related to the port on a switch, nor a port on a IP transaction. It's just a number to uniquely identify this particular channel. And again, in automotive point-to-point or PHY-to-PHY MACsec, you know who the transmitter is always, so the SCI is not necessary. Here's what happens inside of a transmitting MACsec PHY. First, the PHY receives a standard MAC frame from the host media access controller. The frame check sequence is discarded because a new one needs to be calculated. Then the PHY must assemble a sec tag, including ether type of always 88E5. The PHY must look up the correct association number, AN, insert that, and also the correct packet number for this frame. And the packet number gets incremented by 1 because it's going to transmit a new MACsec frame. So the packet number is assembled, the sec tag is completely assembled, and that gets inserted into the frame, increasing the frame's length. Then the packet number is inputted as an initialization vector with padded zeros into the AES crypto engine inside of the PHY. The correct SAK, the correct key, must be looked up based on the association number and also inputted. And then the output, in this example, we're only going to consider authentication. The output of the AES in crypto is the ICV, the integrity check value. That also gets inserted into the frame, and a new frame check sequence is calculated. So now we have a non-encrypted, secured MACsec PDU ready for transmit to the partner PHY. Here's the process that happens inside of the receiving PHY. So the receiving PHY first receives the secured MACsec frame from the link partner, including the sec tag and ICV values. Notice that there's two ICV values here, one in red and one in yellow. The yellow is calculated by the receiving PHY. The receiving PHY then takes the association number in the packet and looks up the correct active SAK. The packet number is taken also, and the frame without the FCS and ICV, the SAK, the key, and the packet number, the same initialization vector that the transmitter used, is all put into the AES crypto. So notice the inputs are all the same as the transmitting PHY. Therefore, if the frame is unchanged, the output of the AES algorithm should be the identical ICV value. So the ICV value calculated by the local receiving PHY then is compared with the one that is transmitted, calculated by the transmitting PHY. If they are identical, then the frame is authenticated. Then the frame is taken, the sec tag is removed, a new frame check sequence is appended to the end of the frame, and essentially what we've done is reassembled the standard MAC frame that the transmitting PHY originally received from its media access controller. Now this frame is a standard MAC frame, and it just gets transferred into the host media access controller of the receiving PHY. Now we're going to shift our focus away from MACsec towards MKA, MACsec Key Agreement. And in MKA, again, we're focused on automotive use cases here, there has to be a key server. The key server generally is statically assigned and is most of the time in the same ECU as the switch itself as part of the Ethernet system. So the key server's responsibility is to generate ephemeral SAKs and deliver them to the appropriate participants. The ephemeral SAKs are temporary, and this provides good protection because temporary keys are difficult to reverse engineer. There's simply not enough data on the network to reverse engineer a temporary key. Additionally, any recording of data, recording of network traffic cannot be replayed in the future because in the future, any pre-recorded data would have a different SAK. There are other keys used in MKA, specifically the ICK. This is the integrity check key used to authenticate MKAPDUs. MKAPDUs are just PDUs that contain control information used to exchange data between the participants of an MKA system. They're not part of the actual data that the user wants to transport. And MKAPDUs should not be confused with MACsec PDUs. MACsec PDUs transport the actual user data. ICK and KEK have key derivation functions, and of note is that there's no random inputs here. The reason why there's no random inputs is because different participants have to calculate independently the same KEK and ICK. These are generated by every individual participant, including the key server. And all of these keys are derived, or potentially can be derived, from the main secret, again, the CAK. You'll see that the CAK is an input to all of these key derivation functions. The SAK, since it is generated by only the key server, a single entity, and transported to the individual participants that need it, it is possible that we can generate an SAK without the CAK. As long as it's a high entropy random number, the system will still function. The ICK, integrity check key, is used to authenticate MKAPDUs, that is the control information as part of MKA. The KEK, the key exchange key, is used to encrypt the SAK. Remember, the SAK is generated by a single entity and needs to be delivered over the network to other entities. And we cannot transmit these ephemeral SAKs in plain text, because then someone could just sniff on the network and see what those SAKs are. So those are encrypted with the KEK. Here's the overall picture of the hardware architecture for an MKA system. We're going to mainly focus on just the key server to one of its peers, and we can replicate the same information for the other peers that exist on the network. So we have a key server, and each participant also has the CAK and CKN, which is just a name for the CAK, statically stored in secure memory. There must be some microcontroller or SoC to run the software stack for MKA in both the key server and each peer. The server uses a key derivation function that we already covered to generate the SAKs, KEKs, and ICKs, and each individual participant generates the ICK and KEK independently. The key server must have some connection to the Ethernet network, and therefore it must have some form of MAC and connection to the switch of the system. It doesn't have to be on the same port as any particular participant, but it has to be on a port, a physical port on the switch. And this is how MKAPDUs will be exchanged. And again, MKAPDUs, which we're going to get into in a minute, are the packets of information that are exchanged between MKA participants. The switch will also have a MAC and a PHY connected directly to the participant itself. So this is where MKAPDUs will be generated from the microcontroller integrated in the key server and in the participants. They also send MKAPDUs and sent through the normal transport mechanism as part of an Ethernet network, normal MAC frames. And we have to keep in mind that the PHYs themselves involved in the MACsec part need the keys installed inside of themselves as well. And this is generally done through a separate hardware interface called MDIO. So the integrated microcontroller inside of the switch will put the SAK and configuration information as part of the security policy into the PHYs that it's connected to physically, and each individual participant will also have a microcontroller that'll do the same thing over MDIO into the PHYs. Here is the structure of an MKAPDU. MKAPDUs are transported within normal MAC frames, so destination, source, optional VLAN, and frame check sequence. And the ether type is always 888E, indicating that this is in fact an MKAPDU. Inside the payload of the MAC frame, we have a header, which just contains a protocol version, packet type, which is always 5 for Automotive MKA, and the length of the packet body in bytes. And the packet body consists of something called parameter sets and also TLVs. Parameter sets are the structured pieces of information that get transferred between peers of an MKA system. And finally, at the end, there's an ICV, which is contained within what's called a TLV, which is a type length value. There are many types of TLVs in MKA, but most of them are not used in the automotive use case. This is one that is used. So the ICV TLV contains a header, but it's a fairly straightforward header. It's always a 255 at the start, reserve bytes, and then just a length of the ICV itself, which is always 16 bytes. The ICV is calculated with the integrity check key. Now let's get into the individual MKA parameter sets. The list of the ones that are used in automotive MKA are listed here. The first is the basic parameter set, and every MKAPDU must start with this basic set, and the following is the structure of the MKA basic parameter set. First, you have a version number, which is currently 3, and for automotive use cases it must be 3 or higher. Key server priority, and this is used for more complex systems where a key server is elected. In automotive use cases, key server is statically assigned. Therefore, the key server must put a 0 here, meaning it's the highest priority to become the key server, and all other entities put in a 255 if they're transmitting this MKAPDU. Then we have 1 bit, which is true for the active key server if it's transmitting this message. MACsec desired, always 1 in MKA, and MACsec capabilities. This tells the system what MACsec capabilities are going to be used. In automotive MKA, we will always use integrity. Authentication is always active. And confidentiality or encryption is optional. And if confidentiality is used, there can be an offset, either 0, 30, or 50 bytes that will not encrypt those particular bytes of the MACsec PDU. The justification for that, or the reason for that, is the bytes can be skipped, thereby exposing the inner ether type and or VLAN so that switches and other entities in the network can act on that information. If they're encrypted, then those values will not be valid. Next, we have the parameter set body length, which comes follow. Next, we have the parameter set body length, which is 12 bits. And then we have the body. First is the SCI, which mentioned before for point-to-point MACsec and MKA. This is not needed. Then we have a member identifier. And a member identifier is a 12-byte unique ID for every participant or entity in the system. And for automotive use cases, member identifiers can be manually assigned. We have a message number. It's a 4-byte monotonically increasing number that increases with every transmit of an MKAPDU by an entity. We have algorithm agility, but 802.1x, the most recent specification, only has 1 number. Then we have the connectivity association key name. Then padding to align the entire piece of information, the entire parameter set, on a 4-byte boundary. The connectivity association key name is used as part of the authentication process that a particular participant is a valid entity to participate in this MACsec system. Every entity needs the CKN and the CAK statically configured. Other parameter sets used in automotive MKA are the live peer list and potential peer list. A live peer list contains a list of the active live peers that have been validated. In other words, that they have the valid CAK and CKN. The CKN is transmitted in every single MKAPDU, and the CAK is implicitly applied in the fact that if an ICV value checks out, if it's calculated correctly and it's verified on the receiver side, it means that the transmitter must have the same and correct CAK. The MACsec SAK use parameter set indicates how a specific SAK is being currently used, whether it's being used for authentication of reception of MKAPDUs or transmission, or both, or not yet in use. The distributed SAK parameter set carries the encrypted secure SAK from the key server to other participants. The XPN parameter set defines optional parameters in case the system is using extended packet numbering. And then there's an announcement parameter set, and this can be thought of sort of like a wrapper for other TLVs in MKA. TLVs, again, are type length values. They contain specific information in a specific structure, but the only one that's used in automotive use cases is the ICV TLV. In this video, we won't take the time to go through every single parameter set, but we will discuss two additional ones beyond the ones we discussed here so that you can have a good understanding of the details of how the initialization and rekey process occurs. The last two parameter sets that we're going to cover is the distributed SAK parameter set and the MACsec SAK use parameter set. The distributed SAK parameter set is the parameter set that delivers the encrypted SAK to individual participants from the key server. It starts off with a type that uniquely identifies this parameter set from other parameter sets, the association number of this secure channel. This is 2 bits, and the key SAK is always associated with an association number. The confidentiality offset, if encryption is used, then we can have no confidentiality offset. We can have a 30-byte or 50-byte offset, again exposing what could be important information to switches and other entities that transmit these MKAPDUs. Then we have the parameter set body length. Then we have a key number. Key number is a 4-byte monotonically increasing number every time the key server generates a new SAK. Then we have the MACsec cipher suite used. The 4 options are here. And finally, the encrypted SAK. The MACsec SAK use parameter set, the use is the key word here, notifies other participants of how a particular key is getting currently used. So here we have, again, the type, which is always 3, just indicates that this is a SAK use parameter set. Then we have the latest key association number, latest key TX, which indicates whether the most recent key sent is being used for MACsec PDUs. And RX, latest key RX, means the latest SAK is used for receiving messages or authenticating messages. Then we have the same thing for the old key association number, old key TX, and old key RX. And these parameters are used specifically during a rekey process where more than one key may be active so that communication is not disturbed. Then we have 2 flags indicating whether the actor is transmitting encrypted data or receiving encrypted data. Next we have delay protect, which is a feature only available for XPN use cases. If XPN is being used, we can set a value, delay protect, that indicates the amount of time window we have for a particular XPN to be valid. Outside of that window, the system assumes that that XPN value is no longer valid. Then we have the parameter set body length. Then we have the body, which is the key server's member identifier, the most recent key number, the lowest acceptable packet number for the latest key, the old key server member identifier, and in Automotive MKA, these 2 numbers will always be the same. There's only one key server. An old key number from the previous key, and the lowest acceptable packet number for the old key. Okay, so hopefully we're going to tie this all together and give you a good understanding of MKA in the final few slides. This is a sequence for initialization, and by no means is it the only one that's valid. Depending upon when the key server is able to communicate versus appear during a power-up sequence, communication may be different than this, but this can be considered sort of a minimal set. A basic parameter set is to be transmitted at a minimum rate of what's called the hello time. And I think the default is 3 seconds, can be changed, but in Automotive MKA, TC17 recommends that this basic parameter set, the hello messages, come out at a fairly fast rate when an ECU comes up out of a power sequence. So it's recommended to start at 20 milliseconds, then 40, then 80, then incrementing, doubling every time until you get to the hello time. And the peer is supposed to do the same thing. So it may be the case with actual implementation that the peer sends messages first. It may be the case that the key server sends it first. Step one is an entity sending the basic parameter set. We'll assume it's the key server in this situation. The peer will receive this message, and the basic parameter set contains the CKN, the name of the CAK, as well as an ICV at the end. And if the peer authenticates the message properly, in other words, the ICV is good, then implicitly the peer knows that the key server has the correct CAK. And the CKN is explicitly checked from the value that's sent in the basic parameter set. TC17 also recommends that during initialization, when an entity receives a message, that it immediately responds to it and does not wait for a timeout of the hello time. So we'll assume that the peer immediately responds with its own basic parameter set and a live peer list. Live peer lists would include the key server in this case, because the peer just validated that the key server is actually a good and valid participant. Therefore, it goes on its list of live peers. The key server then, with this message, can validate that the peer is a good and valid participant and can begin also deriving the ephemeral SAK and association number and message number for the SAK. And the key server, as soon as these items are generated, can immediately install those inside of its own PHY through MDIO. The key server then will send the generated SAK and a distributed SAK parameter set, and also include a MACsec SAK use parameter set. In this particular case, the SAK is not being used yet. Therefore, the latest key RX and latest key TX from the key server will both be 0. The peer then can use the SAK transmitted in this MKAPDU to begin to install in its PHY as well. And as soon as the SAK and other parameters are installed into the PHY, it can say that it is able to receive messages, receive MACsec PDUs using the SAK by indicating that the latest key RX is equal to 1. This tells the key server that it can start transmitting MACsec PDUs. The key server will in turn respond with a MACsec SAK use parameter set with the latest key RX, meaning it can receive MACsec PDUs, and also will be transmitting MACsec PDUs by indicating the latest key TX equals 1. The peer now, in response, create a TX SA and begin transmitting MACsec PDUs to the server. In response to this message, the peer indicates to the key server that it's ready for full MACsec communication, bidirectional, by saying the latest key RX and latest key TX both set to 1. And once the peer and the communication partner both have latest key RX and TX set to 1, they will both start using the latest key for all MACsec communication. And this will be 2 SAs, 1 active for each direction. And then the periodic MKAPDU communication will still continue based on the hello time. So at a minimum, the peers, including the key server, must send at least a basic parameter set MKAPDU and live peer list periodically. And that'll keep the communication active until a rekey needs to happen. In the last slide, we showed what an MKA initialization sequence might look like after a power-up of a system. In this slide, we're going to show how a rekey sequence looks like. Again, there are other valid sequences of rekey events that are good. This is just an example. The key servers are responsible for recognizing when a rekey event must occur. The one important thing that should never happen is the packet number should never roll over. Additionally, there might be time-based parameters or other triggers based on the security policy. First thing that happens is the key server recognizes a rekey needs to happen. It will calculate a new SAK, association number, and install those into the local PHY without disturbing the old keys. So that means Automotive MACsec PHYs have to support multiple keys at one time. The association number is a 2-bit number. Therefore, it's possible with the specification that 4 keys can be active at one time in one PHY. The key server will distribute the SAK in a SAK parameter set and also send a MACsec SAK use parameter set indicating to the peer that it is not yet using the new key. So the latest key RX will be 0, latest key TX will be 0, and the old key RX and old key TX will both be 1, indicating that the old key is still active and completely used. The peer will verify the MKAPDU and thereby validating that the information is correct and begin to install the SAK and associated parameters into its PHY. As soon as those are installed and activated, the peer will indicate to the key server that the latest key can be used for reception with latest key RX equals 1, but will not use it yet for transmission because the peer doesn't know yet if the server is ready to receive MACsec PDUs with the most recent key. So here we still have old key RX equals 1 and old key TX equals 1 from both parties. Once a key server sees that the peer can use the most recent key, it'll start using the most recent key. So the latest key RX is 1. In response, the key server will send to the peer latest key TX equals to 1, as well as the previously sent parameter latest key RX equals to 1. And it'll indicate to the peer that it will no longer use the old key for transmitting by setting the old key TX equal to 0. But yet it can still receive MACsec PDUs generated with the old SAK. So at this particular condition, the key server can receive MACsec PDUs with either the old key or the new key. The peer then will recognize that the key server is able to receive MACsec PDUs on the new key, and in response, it'll set the latest key TX in the MACsec use parameter set that it sends back to the key server. It'll indicate that it's using the latest key for TX and RX, and also indicate that it's no longer using the old key because the peer knows that the key server will be transmitting only with the new key and not the old key anymore. The key server will recognize that the old key RX is equal to 0. In response, the key server will say, okay, let's stop using the old key, and will send a MACsec SAK parameter use set with the old key, RX, and TX both being 0. So at this point in time, both the peer and the key server have indicated that the old key is no longer being used. What will happen is, after a period of time, again, configuration parameter, the old key will simply expire. The old secure association will simply expire based on time, and the new one then will be used. But you can see that there's a period of time when old and new keys are both active and being able to use, thus preventing any disruption in MACsec PDUs. And I can indicate that here by showing that MACsec PDUs are always being transmitted during this entire sequence. And then after that, we still get the hello time messages, the messages that need to be sent to keep liveliness, and wait for a new Rekey sequence to happen. Okay, in conclusion and as a summary, MACsec and MKA work together to provide strong security for Ethernet, automotive Ethernet networks at layer 2. There's broad protection for a wide variety of MAC frames, including all MAC frames. Some frames can be bypassed based on a security policy. We use AES for the main encryption engine, the main cipher engine. And MACsec provides the protection at layer 2 using an ephemeral key. And the ephemeral keys are delivered with MACsec Key Agreement. Key servers is assigned statically in automotive use cases that provides the keys. And there's a communication process that happens with MKA in order to deliver the keys securely throughout the entire system while it's active without disturbing any communication in the process. I really appreciate you making it through all this video. Thank you for your time. Again, my name is Colt Correa. If you have any questions, you can use this contact information and our website at www.intrepidcs.com. Thank you for your time.